Beta oxidation of subsequent acetyl units. Okay, meaning acetyl units are 2 carbon units. So acetyl is 2 carbon, like acetyl coenzyme A is a 2 carbon structure. So the shortened fatty acyl coenzyme A is further oxidized with additional cycles until the entire chain is degraded to acetyl coenzyme A. So we're taking our fatty acids and we're breaking them down 2 at a time. We cleave those bonds to give units of 2. And we run through the citric acid cycle to produce ATP, and we produce coenzyme A, which can be used to regenerate the cycle. Okay? So every acetyl coenzyme A produced enters the reactions of the citric acid cycle, just like we did before. In the citric acid cycle, 12 ATP molecules are going to be produced for every acetyl coenzyme A that's released during beta oxidation. So during the breakdown of fatty acids, it's going to break it down into pairs of 2. So the fatty acid is 20 carbons long. You're going to have 10 sets of 2. If it's 16 units long, you're going to have 8 sets of 2 as it breaks it down. And those are going to run through the citric acid cycle. And each citric acid cycle produces 12 ATPs. And this is from the last lecture, from the last chapter. But as you run through, this is your coenzyme A, acetyl coenzyme A right there, and it runs through the citric acid cycle. And as it spins, it produces 3 NADHs. Okay, there's your NADH, there's your NADH, there's your NADH. It produces 1 GTP and produces 1 FADH2 as you run through the cycle, right? Remember that? Here's your GTP produced, and here's your FADH2 produced. Right? So now you've produced all those, and remember NADH is 3 ATPs. Okay? And then mitochondria, GTP is 1 ATP, FADH is 2, where it enters that. So this gives you 9 plus 1 plus 2, which is 12. And there's where your 12 comes from. So every turn of the citric acid cycle is going to produce 12 ATPs for every acetyl coenzyme A. If you have 2 acetyl coenzyme A's, you're going to produce 24 in that cycle. Okay? So every acetyl coenzyme A runs through that cycle, and it's going to produce 12 ATPs for each coenzyme A that runs, every 2 carbon units. Does that make sense? That's basically where we left off last time with the citric acid cycle. Cool. All right. So let's do palmitic acid. Palmitic acid, this is from palmitic acid. Okay. So if you look at the formula, how many carbon atoms does palmitic acid have? It's CH3, 14 CH2 groups, and then a carboxyl group. So we've got 16 carbon atoms. Does everybody see that? Someone put a thumbs up or something. Everybody sees we have 16 carbon atoms, right? Perfect. All right. Thanks, Jessica. So 16 carbon atoms. So it's going to break into 8 sets of 2 when we oxidize it. The first step, is going to take ATP and produce AMP. Okay, so that's minus 2 ATPs because it goes from ATP to ADP, ADP to AAMP, adenomyosin phosphate. So basically uses up 2 high energy phosphate bonds to get it started. So at the end of it here, we're going to produce here, this is what we're going to have to subtract from it. These are your 2 high energy phosphate bonds that were input to start That's where this comes from here. Okay, that's where we subtract 2 because it takes 2 to get it started. Okay, we attach the coenzyme A to it, it becomes our coenzyme A complex, and we get beta oxidation, and we break it down to 8 acetyl coenzyme A's. Okay, now when you do that, there's 16 carbon atoms. So let's put 16 carbon atoms here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 carbon atoms. Now you're going to cleave that in 2 carbon atom pieces. Okay. So how many joints did you cleave? You've cleaved 1, 2, 3, 4, 5, 6, 7. So every time the bond is broken, it produces an FADH2 and an NADH. So you're going to produce 7 FADHs and 7 NADHs as you break the bonds into clips of 2. Okay. If you have 16, you're going to have 7 bonds being broken. If you had 18, okay, you're going to have 8 bonds, and you have 18 of them, you're going to have 8 bonds being broken. Okay. If you had 20, you're going to have 9 bonds being broken. Okay, because it has to cleave in sets of 2. Okay, so there's our 2. So you have 7 FADHs, and every FADH is times 2, every NADH is times 3. So for each of those bonds that are being broken, you've released 14 ATPs, or you generate 14 ATPs, and 21 ATPs for the NADHs. Okay, so there's 14. Now each of those two carbon units, okay, is going to be an acetyl coenzyme A, and it's going to enter into the citric acid cycle. So you're going to have 8 acetyl coenzyme A's entering in the citric acid cycle. Okay, it's 16 carbons, 8 sets of 2. Okay, so for every spin of the citric acid cycle, we produce 3 NADHs, 1 FADH2, and 1 GTP, just like we had in the picture before. Okay, and the NADHs, we're going to go through 8 times, so we're going to produce 24 of them. The FADHs, we're going to go through 8 times, we're going to produce 8 of them. And the GTPs, we're going to produce 8 of them. Okay. So for every, so for every turn we have here, okay, it's going to produce 24 NADHs and then times 3, which gives you 72 ATPs. FADH is times 2, GTP is times 1. Okay, so we add that together. Okay. We've got 14 from this FADH2. We have got 21 from these NADHs formed when they cleave the bonds. We've got 24 times 3, which is 72, from this run through this, from this NADH form. And then from this FADH2, we have 16, we have 8 times 2, which is 16. Okay. And then you run 8 from the GTP over here. We add all that together. Okay. 7, 50, what do we got? 14, 16, 17, 21. So we have a 1, carry the 2, 3, 5. And I think that's 9, 10, 11, 12, 13. 131 ATPs. Okay. So running the citric acid cycle 8 times with the oxidation of palmitic acid, which has 16 carbon atoms, we're going to produce 131 ATPs. Now it took 2 to get it started. We lost 2 high energy bonds when ATP here went to AMP. Okay, so we subtract 2 from it. So we end up with 129 ATPs as our net production. Okay. So complete oxidation of palmitic acid gives you 129 ATP. We'll take all the looks and take a look at that. So if we know how many carbon atoms are in the fatty acid, we can tell you how many ATPs are going to be produced by the oxidation or the breakdown of that fatty acid. Because that's how our body stores energy. That's left over. We store in the form of triglycerides, which are fatty acids bond to a glycerol molecule, and you have 3 long fatty acid chains into every glycerol molecule. That's what we store as fats for energy. Okay, so we're going to do a couple examples of how we break different fatty acids down to form ATP. But that's the basic what we do right there. Okay, so the first step always uses up two phosphate energy, high energy bonds, phosphate energy bonds, where ATP goes to A and P. Then we cleave it into 2 unit sections. Every time we break a bond, it releases energy. 1 FADH, 1 NADH. Every NADH is worth 3 ATPs. Every FADH2 is worth 2 ATPs, where it enters a cycle. Then we run every 2-carbon chain, every 2-carbon segment we have through the citric acid cycle. Okay. We produce NADH, we produce 8 of them. Okay, if we're gonna, well, for every turn of citric acid, we're gonna produce 3 NADHs, 1 FADH2, and 1 GTP. We're gonna run it 8 times for palmitic acid. We're gonna produce 24 NADHs. We're gonna produce 8 FADH2s and 8 GTPs. Okay, GTP is 1 to 1. FADH2 is one of those, goes to 2 of those, and 1 NADH produces 3 ATPs. Add all that together, and then subtract our 2 from the unit that you had to input, and you get your total. And that's how we're going to do it. All right. So this is the breakdown what we did. The first, what was activation? We added coenzyme A to make a coenzyme A complex. Palmitoyl acid coenzyme A. So we subtracted 2 ATPs. Okay. Our first step is breaking it into 8 pieces. That means there's 7 bonds being broken. Okay, so you're going to form 7 FADH2s, and each one of those gives you 2 ATPs. That's 14. Okay. Then you're going to form that's your FADH2. You're going to form your NADH. Again, there's 7 bonds being cleaved. You're going to form 7 NADHs. Okay, and each one of those is worth 3. So you get 21 ATPs. Now you enter the citric acid cycle. Okay. Citric acid cycle produces 1 GTP, 3 NADHs, and 1 FAD for every turn, every cycle it runs. And you're going to have 8 cycles. So we multiply each of those by 8. That's where this 8 came from here. And you end up with 8 ATPs from your GTP, 72 ATPs from your NADH, and 16 ATPs from your FADH2. So add all that together and subtract 2, you get 129 ATPs. And that's how it's calculated, just like that. Is that making sense? I hope. All right, perfect. So what products would be produced by the beta oxidation of 10-phenyl-decanoic acid? Decanoic acid is 10 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's decanoic acid. Okay. And 1, 2, 3, 4, 5, 6, 7, 8, 9. At the number 10 position, there's going to be a phenyl group. Your phenyl is a benzene ring. Okay. So oxidation, you're going to break it down into 2 sections. Do carbons. So let me get that out of the way. Okay. Okay, so the 10-carbon fatty acid chain broken into 4 acetyl coenzyme A molecules. That take care of 8, then the other 2. Then you get 1 phenyl acetate. Okay, let's break it out like this, maybe make a little more sense. 3, 4, 5, 6, 7, 8, 9, 10. Okay, and at number 10, there's a phenyl group. And these are hydrogens. CH2, 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 CH2. Okay? So you're going to break them down into groups of 2. You're going to break 1 here, 1 there, 1 there, 1 there. So you're going to get 1, 2, 3, 4 acetyl coenzyme A groups. And you're going to 1 acetyl, okay, 1 phenyl acetate group, because you got a phenyl group attached here. Okay, so that's the complete breakdown of 10-phenyl decanoic acid. Okay, because 4 cycles through beta oxidation are required to break down a 10-chain fatty acid, you're going to produce 4 NADH molecules and 4 FADH2 molecules. Okay, because you're broken up, you're having 4 bonds, right? 1, 2, 3, 4 bonds. Every one of those bonds that breaks produces a FADH2 and a NADH. Okay, so that's a total product being formed. And then your pseudocoenzyme A is going to run through the citric acid cycle to produce more ATPs. So the products being produced by beta oxidation of 10-phenyl decanoic acid is going to be 4 acetylcoenzyme A molecules and 1 phenyl acetate molecule and 4 NADHs and 4 FADH2s. And then it goes through the citric acid cycle. Okay. Any questions on that? Because it's important to see how those break down. Okay. So what products will be formed by beta oxidation of each of the following fatty acids? So we can write down each one. 9-phenyl nonanoic acid. Okay, that's a phenyl group and 9 carbons. 8-phenyl octanoic acid, 8 carbons. Number 8 has a phenyl group. 7-phenyl heptanoic acid and 12-phenyl dodecanoic acid. Okay, so let's do the first one. 9-phenyl nonanoic acid. So how many carbons? Nonane is 9. Oic acid. Okay, so 9 carbons. 9 carbons. Okay, and at number 9, there's a phenyl group. There's your benzene ring. And this is your acid right there. Okay, so we're going to break those bonds out. We're going to break down 2 carbons, 2 carbons, 2 carbons, and then 2 carbons. Okay, so you're going to end up with 4 acetylcoenzyme A's right here. 1, 2, 3, 4. Those are your 4 2-carbon units. You're going to have 1 benzoate. This is your phenyl group bonded to carbon. Okay, your benzoate. You're going to have 4 NADHs, because every one of those bonds here is going to produce a NADH and an FADH2 and 4 FADH2s. So that's what you're going to have from 4-phenyl nonanoic acid. And each of those 4 coenzyme A's are going to run through the citric acid cycle to produce ATP. Okay. And it's going to produce, each rotation produces 12 ATPs. NADH is going to produce 3 ATPs for each one, so that's 12. FADH2 produces 2 ATPs, so that's 8. Okay. All right, 8-phenyl octanoic acid. Octanoic acid is 8 carbons. Okay, so here's your 8 carbons. Here's your carbonyl carbon and your carbonic acid. Okay, and at 8, there's a phenyl group again. And we're going to cut that into sections of 2 when we break it down. So there's your first 2, your next 2, your next 2. So you're going to have 1, 2, 3 acetyl acid groups. You're going to have 1 acetylbenzene group. You're going to have 3 NADHs, and you're going to have 3 FADH2s, 1 for every bond. Right? So 3 acetylcoenzyme A's. Those are these 3 units right here, 1, 2, and 3. You have 1 phenyl acetate, which is this unit right here. And then for every bond that you broke, there's 3 bonds being broken. Look at the green lines. You're going to have 1 NADH and 1 FADH2. And then these are going to, and then the acetylcoenzyme A is going to run through the citric acid cycle and produces 12 ATPs for each spin. and 7-phenylheptanoic acid. Heptanoic acid is 7 carbons. So there's 1, 2, 3, 4, 5, 6, 7. And it's 7-phenyl. So it's a phenyl group at number 7. Okay. Oxidation, we're going to break it down into acetocoenzyme units into 2 carbon groups. So there's 1, there's 2 carbons, there's 2 carbons, and there's 2 carbons. So we use up 3, we cut 3 bonds, broke 3 bonds, and we have 1 acetocoenzyme A, 2, and then 3. So you're going to end up with 3 acetocoenzyme A's. You're going to end up with 1 phenylbenzoate. That's what's left with the phenyl ring on it. You end up with 3 NADHs and 3 FADH2s. Okay, 1 for every bond formed. Okay, so 3 acetocoenzyme A's. This is your 1, 2, 3 right there. 1 benzoate, that's this group right here. 3 NADHs and 3 FADH2s, 1 for every bond that's broken. So 1, 2, 3 bonds are broken. Remember, every NADH gives you 3 ATPs. Every FADH2 gives you 2 ATPs. Every acetocoenzyme A run through the citric acid cycle gives you 12 ATPs. Because it gives you 3 NADHs, 1 FADH2, and 1 GTP. Okay. I think I had one more to do. Phenyldodecaenoic acid. Dodecaenoic acid is 12 carbons. So we have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, put 12 out here. There's your bond. And then at number 12, we have a phenyl group. I don't know if the phenyl group does it. I should do better than that. Okay. So there's number 12. There we go. That looks better. So we're going to break this down. Beta oxidation is dissolving into units of 2 carbons to run through the citric acid cycle. So here's 2 carbons. There's 2 carbons. Yeah, 1, 2, 2, 2, 2, 2. Everything's broken down to 2 carbons. Okay. So we're going to have 1 acetyl acid, 2, 3, 4, 5 acetyl acid groups. Okay. We're going to have 1 acetylbenzene group. That's this right here. And we had broken 1, 2, 3, 4, 5 bonds. We break 5 bonds. We have 5 NADHs and 5 FADH2s. So there we go. 5 acetocoenzyme A, those are the 5 right here. 1, 2, 3, 4, 5. 1 phenyl acetate, which is this circle group right here. Then for every bond that was broken, we broke 5 bonds. We get the NADH and an FADH2. Right? And that's going to allow you to predict the cycle through the citric acid cycle, how many ATPs are going to be formed from each fatty acid. Okay, so how many moles of ATP are produced in the complete oxidation of stearic acid? Stearic acid is 18 carbon saturated fatty acid. Okay, so we have 18 carbons. So you're going to break it into groups of 9 double carbons, 9 acetocoenzyme A's, and you're going to have 8 bonds being broken to form that. Okay, so you're going to produce 9 acetocoenzyme A's. You're going to break 8 bonds. So you're going to produce 8 NADHs and 8 FADH2s. And it takes 2 to initiate to get started. So let's get that out of the way here. Remember, we have to activate it first. So our activation is going to be minus 2 ATPs. And then the first step is going to be to break it into 2 carbon sections. So you're going to have, you have 9 You have 18 carbons. So we're going to have 9 coenzyme A's, acetylcoenzyme A's. Okay. So we have 8 bonds being broken to break it into 2 carbon segments. So we have 8 FADH2s and 8 NADHs. Every FADH2 is worth 2. Every NADH is worth 3. So 16 ATPs from the FADH2 and 24 ATPs from the NADH cycle, NADH. Now you got 9 acetylcoenzyme A's going to the citric acid cycle. Okay. Remember, every spin, we're going to have 12. Let's see, where we at 12. Yeah. For every spin, we have 12 ATPs produced. Remember, we get 1 GTP, 1 FADH2, and 3 NADHs. And we're going to spin that how many times? We're going to spin that 9 times. So you can do it. You can do 12 for every spin and 9. 9 times 2 is 18, is 108, right? Does it come to 108? Yeah, 18. Okay. So we have 108. Yeah. And then we're going to subtract 2. So you have 108 plus 16 plus 24 comes out to 18, 148. And then we're going to subtract 2. We're going to get 146. Okay. So 146 ATPs are made by an 18 carbon saturated fatty acid, which is stearic acid. Okay. So you can break it down either way you want. You can run it through. You can realize that there's going to be 12 ATPs produced per citric acid cycle, or 1 GTP, 3 NADHs, and 1 FADH2. And this is a GTP gives you 1 ATP, an NADH gives you 3, and an FADH gives you 2. And you're going to run it 9 times. Or you can say that there's 12 ATPs produced every cycle, and you run 9 cycles. So this is 108, this is 108. Either way is the same thing. And then it takes 2 to start activating it. So 146 ATPs are produced for every stearic acid that's broken down. Remember, that's just 1 fatty acid on the triglyceride. There's 3 more. There's 2 more, because there's 3 on each glycerol molecule. So it's a very efficient way to store energy that we can produce for ATP when the body needs it. Okay, write the sequence of steps for beta oxidation of butyryl coenzyme A. What's the energy yield from the complete degradation of butyryl coenzyme A via beta oxidation, citric acid cycle, and oxidative phosphorylation? All right, butyryl coenzyme A is going to be 4 carbons. Okay, so here's your 4 carbons. This is butyl, your coenzyme A. Okay, it takes an FAD and it produces an FADH2, then uses the water to make your complex. Okay, because you got to hydrate that bond right there. Remember, hydration attached to the bond, you get an OH and an H on each side of the double bond. Okay, and that's going to form your acetyl group here. Okay, then you're going to add your NADH to form your NAD, plus to form NADH. Okay, then come back. Then your coenzyme A reacts to that to form 2 acetylcoenzyme A's. Okay, because this is going to break into 2 carbon, because acetylcoenzyme A is 2 carbon chains. So we start with butyl. Okay, butyl is 4. You end up with 2 coenzyme A's to run through the citric acid, acetylcoenzyme A's. Okay, and you're going to break 1 bond. You're going to form 1 FADH2 and 1 NADH. And this is going to be times 2. That's going to be times 3. Okay. And now the energy yield from it. Okay. So there's our butyl coenzyme A. We ended up with 2 acetylcoenzyme A's. We broke the 1 bond. We formed an FADH2 and an NADH. So the FADH was 2 ATPs, NADH was 3 ATPs. We're going to run through the citric acid cycle. We have 2 coenzyme A's. Okay, so there's 12 for every spin, and we're going to spin it 2 times. So you're going to end up with 24 ATPs. Okay. And where's our GTPs? So 24 and 5 is 29. I'll include all that in there. So this is your GTPs right here. That was formed. This is your FADH2. And this was your NADH. So basically it's a 4-carbon fatty acid chain, butyl coenzyme A. And you're going to break it down into 2 carbon chains just like we do all the other fatty acids and run through the same exact cycles. Okay. Any questions on that? Everybody understands that completely. What you have to know for the exam is that any fatty acid is going to be broken down into 2 carbon sections. Every bond you break to form a 2-carbon section gives you an NADH and an FADH2. Okay. Then it's going to run every 2-carbon section. It's going to run through the citric acid cycle. Every time one of those things runs through the citric acid cycle, it produces 3 NADH, 1 FADH2, and 1 GTP, which is 12 ATPs. Okay. So you add those 12 together, multiply by how many times you run the cycle, you add what you get from breaking the bonds. Okay. You really had 2 to initiate it, so you subtract 2 from it, and that's your total ATPs for any fatty acid you can do now. Okay. So ketone bodies. Ketone bodies are bodies that are carbon compounds that have a ketone in them. Okay. If you look at this, this is acetone, which has a ketone, acetoacetate, which has a ketone. Okay. So results of excess acetocoenzyme A from beta oxidation. So you got extra acetocoenzyme A, you're going to form ketone bodies. When glycolysis and beta oxidation occur at the same rate, there's a steady supply of pyruvate to convert to oxaloacetate. Remember, that runs the citric acid cycle. Okay, because all your glucose is converted into 2 pyruvates. And that pyruvate gets into oxaloacetate, which runs the citric acid cycle. So if the supply of acetylacetate is too low to allow all the acetocoenzyme in the citric acid cycle, it builds up. Okay? So if you don't have enough acetylacetate to keep the citric acid cycle running, okay, your acetocoenzyme A is going to be built up because it can't run through the citric acid cycle without bonding to oxaloacetate first. Okay? So then you can have extra acetocoenzyme A. If you have extra, it converts it into what's called ketone bodies. Ketone bodies are beta, hydroxybutyrate, acetone, acetoacetate. And those are all 3 on the bottom right here. You can see their structures. I count. Okay. So ketosis occurs. Ketosis is when abnormally high levels of blood ketone bodies are present. Okay. Arises under some pathological conditions like starvation. Starvation, you don't have enough oxaloacetate to run the citric acid cycle. So your pyruvate converts to acetocoenzyme A. The acetocoenzyme builds up because it can't run through the citric acid cycle, and you get ketone bodies. In a condition called ketosis. Okay. It occurs under starvation, like we said, extremely low in carbohydrates. Okay. The very high protein diets you have, the Atkins diet we talked about. The Atkins diet produces a negative nitrogen balance. Okay. So very low carbohydrate diets produce, okay, ketone bodies. Uncontrolled diabetes produces extra ketone bodies. Okay. So uncontrolled diabetics can have very high concentration of ketone acids in the blood. Okay. You can get ketoacidosis. And ketone acids are relatively strong acids that release H+. H+ can then lower the pH of the blood. So when blood pH then becomes acidic, it lowers pH, Your enzymes don't work and it leads to death. Okay? So ketoacidosis in uncontrolled diabetes can lead to death because of the ketone bodies produced. Okay? Because you get ketoacidosis and those are strong acids. Ketogenesis, okay, is production of ketones bodies begins with the reversal of the last step of beta oxidation. So instead of going to produce acetylcoenzyme A, because then we have excess acetylcoenzyme A because oxaloacetate is not present, okay, acetylcoenzyme A can produce acetylcoenzyme A, which it makes, instead we have to have 1, 2, 3, 4 carbons now. So acetyl is a 2-carbon group, acetyl is a 2-carbon group, so that's a 4-carbon group, and coenzyme A. So you have two carbon groups fusing together with your coenzyme A. Okay? And that's called acetyl coenzyme A. And it's made from 2 acetylcoenzyme A molecules that are building up in the body. And this is a ketone body. Here's your ketone right here. Here's your ketone right here. So those are ketone bodies. Okay? So this is a reverse step of how you make acetylcoenzyme A. When oxaloacetate levels are low, 2 acetylcoenzyme molecules are fused to form an acetylcoenzyme A. Okay, remember, when oxaloacetate is low, you're not going to run the citric acid cycle because you need that to bond to the coenzyme A. So you build up coenzyme A, you get too much of it, it starts to form acetyl coenzyme A. Okay. Combination of acetyl coenzyme A with a third acetylcoenzyme A yields beta hydroxy beta methyl glutarate glutarate coenzyme A, HMG coenzyme A. Okay. So here's your acetylcoenzyme A. You're going to add another acetylcoenzyme A. Now you're going to make it into a 6-carbon chain. Okay. So now you got 6 carbons in the chain. Okay. And you form HMG coenzyme A. HMG coenzyme A formed in the cytoplasm is a precursor for cholesterol biosynthesis. And this starts to make cholesterol in the body and store it as a fat in the body, as cholesterol. Okay. So we're adding a third acetylcoenzyme A to this to one that already has 4 of them. Okay. In mitochondria, HMG coenzyme A, okay, is cleaved to yield acetoacetate and acetylcoenzyme A. So this goes into the reverse cycle back in the mitochondria where it cleaves it and reforms acetoacetate and acetylcoenzyme A. And acetoacetate is a ketone body. Okay, so it took back off that original coenzyme A and left this with 4 carbons. Okay. Acetoacetate, small amounts of acetoacetate spontaneously lose carbon dioxide to produce acetone. Okay. So when you have small amounts of this in the body, you're going to lose your carbon dioxide and you're going to produce acetone. Acetone, you can also smell, is called acetone breath. Acetone has a specific smell. Paint thinner, paint remover is acetone. And it's often associated with uncontrolled diabetes. Some of your patients will have their breath, you smell the breath, they smell like acetone. That's an indication of acetoacetate being broken down, okay, producing acetone. There's a condition of uncontrolled diabetes. Okay. Particular reaction has acetoacetate reduced in an NADH dependent reaction to produce beta hydroxybutyrate. Okay. So the ketone bodies, which were acetoacetate, acetone, and beta hydroxybutyrate. Those are your ketone bodies. Now the heart, okay, heart muscle's main energy source is from ketone body oxidation, the breaking down of those ketone bodies. Okay, they can be converted into acetylcoenzyme A. We just saw in the mitochondria. They're produced in the liver. They diffuse into the blood, and they circulate to other tissues in the form of cholesterol. So acetoacetate reactions, acetoacetate can give off carbon dioxide and form acetone. Okay, spontaneously gives it off. So when acetoacetate is formed because you're starvation, diabetes mellitus, okay, you can get acetone breath. That's one of the things you look for in a diabetic patient. Okay. Acetoacetate can also react with NADH to oxidize it back to NAD plus, okay, and form beta hydroxybutyrate. Okay. So this is reaction of ketogenesis. We started with 2 acetylcoenzyme A's, because you remember the oxaloacetate is getting too low, so you cannot run the citric cycle. So these normally go into the citric acid cycle. Okay. But if oxaloacetate is too low, this won't run. So now they combine together. 2 of these combine to form acetylcoenzyme A. Okay. It can add another one to it and get beta hydroxy, beta methyl glutarate coenzyme A. Okay. This can give off another acetylcoenzyme A and form acetoacetate, which can spontaneously give off carbon dioxide to form acetone. And that's what you smell in your patient's breath when they have uncontrolled diabetes, is that acetone right there. Okay. You can react the acetoacetate, can react with NADH, it can oxidize back to NAD plus, okay, and form beta hydroxybutyrate. It's another byproduct of it. That's your ketogenesis right there, the formation of ketone bodies. Okay. So what conditions lead to excess production of ketone bodies? Anything that stops the citric acid cycle from spinning. Okay. Starvation or a diet low in carbohydrates. Low in carbohydrates infers high in proteins. So be very careful of your high protein diets. We don't mix in carbohydrates. You have to balance your diets. Okay. If you just do high protein, low carbohydrates, you'll lose weight, but then you put yourself in what's called negative nitrogen and you're producing ketone bodies. Okay. So starvation will produce excess production of ketone bodies. Low carbohydrates in your diets can produce it, and diabetes, uncontrolled diabetes, okay, that lead to the production of ketone bodies. What is the cause of acetone breath? That's associated with uncontrolled diabetes mellitus. We talked about that. That's the acetylcoenzyme A breaking down. So uncontrolled diabetes causes ketogenesis. Okay? Some of the acetoacetate loses their CO2, okay, to produce acetone. Okay? That causes the acetone breath associated with uncontrolled diabetes. Okay? Fatty acid synthesis. We talk about fatty acid breakdown. Fatty acid breakdown makes a lot of ATP. That's how we store energy, is in our fatty acids. Okay, so all organisms can synthesize fatty acids. That's how we store energy. Excess acetylcoenzyme A from carbohydrate degradation is used to make fatty acids. Okay, fatty acids are stored as triglycerides. Remember, glyceride is 3 carbons. And your fatty acid long chain is stored into each of those 3 carbons. There's 3 of them. Reaction occurs in the cytoplasm of the cell. The acyl group carrier is acyl carrier protein, ACP. That was carries a 2-carbon group, is your acyl carrier protein. Synthesis by addition of 2 carbon units at a time. That's why most of your fatty acids are even numbers. Okay. So it carries a 2-carbon change to the triglyceride is the acyl carrier protein, and it links onto the fatty acid chain that's growing 2 carbon units at a time. Just so we break down 2 carbon units at a time, we add on 2 carbon units at a time. Same thing. Synthesis by a multi-enzyme complex known as fatty acid synthase. And ADPH is our reducing agent now. Okay, that causes reduction, that gets oxidized. And that's a phosphate bond for the hydrogen, NADPH. Okay. So beta oxidation and fatty acid biosynthesis. Beta oxidation is a breakdown of fatty acids, 2 at a time. Fatty acid biosynthesis is a formation of fatty acids, 2 at a time. So inside the cell, intracellular, biosynthetic enzymes are in the cytoplasm and degradative enzymes are in the mitochondria. Okay, so in the mitochondria, because the mitochondria produce ATP, right? That's what mitochondria do. They produce ATP. 95% of all the body's ATP is produced in the mitochondria. So the degradative enzymes are going to be in the mitochondria where you can break down the fatty acids to produce the ATP you need. When you're going to make the triglycerides, biosynthetic enzymes are in the cell cytoplasm. The acyl group transfers, the acyl group carriers. Biosynthetic carrier is the acyl carrier protein, ACP. Okay. Degradative carrier is coenzyme A. We bind coenzyme A to activate it, and coenzyme A runs it through the citric acid cycle. Enzymes involved in it, and biosynthetic complex is a fatty acid synthase, and the degradative enzymes not associated in a complex. Those just the degradative enzymes that chop the two carbon groups off of the fatty acid. Electron carrier is biosynthetic process uses NADPH. The degradative process uses NADH and FADH2 and also GTP. That's our degradative process we use in the citric acid cycle. Okay. So here's your comparison: biosynthesis and degradation, breaking apart. Biosynthesis occurs in the cytoplasm. We use the acyl carrier protein, fatty acid synthase complex, and NADPH electron carriers. For breaking it down, for degradation, again, remember this is 2 units at a time. We're building it 2 units at a time as we're breaking it down. Mitochondria is where the degradation occurs because that's where you're making energy. Coenzyme A is the carrier group. No enzyme complex is formed. Okay, and electron carriers and the degradation of it, beta oxidation, is NADH and FADH2. Okay. So fatty acid synthesis, making of the fatty acids, malonyl ACP, acetyl carrier protein, is produced in 2 reactions: carboxylation of acetyl coenzyme A, you add a carboxyl group to it, and the transfer of malonyl acyl group from malonyl coenzyme A to acetyl carrier protein, ACP. And there's 4 other reactions we have to consider. We have to condensation, which is acetyl carrier protein. Reduction is beta hydroxybutyryl ACP. Dehydration, crotonal ACP, and reduction, which is butyryl ACP. Those are the other actions involved in fatty acid synthesis. Okay. So formation of acetyl coenzyme, we'll break down each one of them. So this is a formation here, acetyl ACP. So formation of acetyl ACP, acetyl carrier protein. Okay. So we have acetyl ACP, okay, plus malonyl ACP. Get a condensation reaction, you give off CO2 and ACP, and it forms acetyl ACP. Okay. So you're adding the 2 carbon groups at a time. You're adding your carbonyl group here. Okay. You've started out with your 2 carbon group, and you've added 2 carbons this way to make a 4 carbon group. That's how you form fatty acids. This is one we find through the acetyl carrier protein, ACP. Okay. Okay. Beta hydroxybutyrate, ACP. So again, we're going to start with acetyl ACP. That's our 4 carbons. With a reduction of NADPH and NAD+, and you're going to form beta hydroxybutyryl ACP. Formation of crotonal ACP. You have beta hydroxybutyryl ACP. Okay. Dehydration reaction, you can lose water. Okay. Between this bond right here, you're going to kick off an OH and one of those H's and form a double bond. Okay. And then you're going to form crotonal ACP as you form your double bond right here by kicking off water, by dehydration reaction. Okay, that forms crotonal ACP. And the last one is the formation of butyryl ACP. Remember, butyryl is a 4 carbon ACP group. So crotonal ACP, and you go reduction to get rid of the double bond here. You can reduce that double bond by adding hydrogen across it. And you can use NADPH for the reduction. Okay. So you get a reduction reaction and you get your butyryl ACP, 4-carbon group. List 4 major differences between beta oxidation and fatty acid biosynthesis. Remember, they're the reverse of each other. That the two processes are not just reverse of one another. They're opposite, but they have different intermediates. Okay. So 4 major differences. First one is fatty acid biosynthesis occurs in the cytoplasm. Beta oxidation occurs in the mitochondria where ATP is formed. Okay. The acyl group carrier in fatty acid biosynthesis is ACP. The acyl group carrier in beta oxidation is coenzyme A. So in fatty acid biosynthesis, we use ACP to add 2 carbon units at a time to a fatty acid. In beta oxidation, we use coenzyme A to run through every 2 carbon piece to run through the citric acid cycle. Okay. And the third one, the 7 enzymes of fatty acid biosynthesis are associated as multi-enzyme complex called fatty acid synthase. You form a complex with the different enzymes. The enzymes of beta oxidation do not form a complex. Okay. So they're not physically associated with one another. They don't form this complex that goes into it during the formation. Okay. NADPH is reducing agent for fatty acid biosynthesis. NADH and FADH2 are produced by beta oxidation. So there's 4 major differences between biosynthesis of fatty acids and breakdown of fatty acids by beta oxidation. They're not just reverse of each other. They use different intermediates and different carriers. It's the effect of being reversed. One adds 2 proteins at a time, one takes off 2 proteins at a time. One adds 2 carbons to a chain, one takes off 2 carbons from the chain at a time. Okay, so they have the exact opposite results, but they're done in different ways. Okay, they're not just the reverse reaction. Okay, so what chemical group is part of coenzyme A and acetyl carrier protein and allows both molecules to form thioester bonds to fatty acids as they build that? Okay, so both ACP and coenzyme A have the phosphopanethine group. It allows the formation of the thioester bond with fatty acids to allow those to build. And that was the sulfur group that you saw, and they're bonding to it. Okay, so both those use sulfur in binding the ACP, binding the coenzyme A to the groups. Okay. Regulation of lipid metabolism. Metabolism of fatty acids occurs to a different extent in different organs. Okay. Some organs are keyed up to specifically designed for metabolism and breakdown of fatty acids. Okay, you have different areas it occurs. It occurs in the liver, it occurs in your fat tissues, you have adipose tissue, occurs in muscle, and it occurs in brain. Okay, so representation of liver and lipid metabolism. So in your liver after a meal, okay, so stimulated by insulin, you absorb glucose. You eat, that's not coming through real clear. You eat a meal, everything breaks down, it breaks down to glucose in the bloodstream. As glucose increases in the bloodstream, your body, the pancreas releases insulin. Insulin causes glucose to be absorbed by the liver. Okay, it converts to glucose 6-phosphate, like we said before it goes into pyruvate. Okay, we can either use it as fuel, convert right on the spot there, or we convert it into glycogen. Glycogen is our long-term storage molecules for glucose. Okay, or we can take it and cause fatty acid synthesis. Fatty acid synthesis is your very low density lipid proteins. It contains fatty acids, and it goes to the adipose tissue. Okay, that's your cholesterol. Okay, after your overnight fast, in the morning, when your body does not have sugar, okay, you produce, the body doesn't, there's low sugar in the blood, the pancreas produces glycogen. Glycogen is the opposite of insulin. It causes glucose to be released back into the blood to get you, so you don't hypoglycemic. And again, the glycogen breaks apart into glucose 6-phosphate, which forms glucose, which goes back into the blood. Okay, it's the exact opposite reaction, because glycogen stores your glucose. The glycogen also releases it, glucose 6-phosphate, to glucose back into the bloodstream. Okay, you can also get fatty acids from your adipose tissues. You can come back as fatty acids used by liver as fuel. Okay, so it reverses the reactions depending whether you have done the blood has high blood sugar or low blood sugar. High blood sugar, you release insulin, and this is what happens. Low blood sugar, you release glycogen, and glycogen, this is what happens. So insulin lowers your blood sugar, glycogen raises your blood sugar. Okay, so when excess fuel is available, the liver synthesizes fatty acids. So when you eat more than you use, it's got to go somewhere, and you start making fatty acids. Fatty acids produces triglycerides that are transported from the liver to your adipose tissue by the very low density lipid complexes. So in starvation or fasting, fatty acids converted to acetoacetate, and the ketone bodies, remember, are exported to other organs for oxidation to ATP. Okay, so you don't have the rest of the regular glucose to run the Krebs cycle to produce pyruvate, to produce acetocoenzyme A. Okay. In adipose tissue is a major storage for fatty acids. Those are your triglycerides. They're stored in adipose tissue. Fatty acid from the liver are sent to what's called adipocytes. Adipocytes are cells that store adipose, store fat. Those are your fat cells. They're called adipocytes. Lipases are under hormonal control and determine the rate of triglyceride hydrolysis, the breakdown. Remember, ASE endings are enzymes. So it breaks down triglycerides. It's controlled by hormonal control, how those are broken down. The synthesis of triglycerides require glycerol 3-phosphate and benzoyl glycolysis to produce that glycerol 3-phosphate. So when you synthesize the triglycerides, you have to be able to break that glucose down into glycerol 3-phosphate to be able to store it. So in the adipose cell, this is your adipocyte right here. You take glucose from the liver. Okay, goes into, it takes glucose is produced by the liver into the blood, goes into the adipose site, converts to glycerol 3-phosphate, converts into triglyceride. Triglyceride then goes to either glycerol and produces glycerol back in the bloodstream, or goes to fatty acids and takes fatty acids back to the liver. Okay. Fatty acids coming from the liver, okay, or coming from the production in the adipocyte here, it breaks down the fatty acids. Because remember, all a triglyceride is 3 fatty acid chains attached to a carbon chain. So you get fatty acetocoenzyme A, and that goes to your triglycerides. Your lipase breaks it down into either fatty acids or glycerol. And that's how an adipose cell works. Okay, that's where your adipose is for your fat, your triglycerides. In muscle tissue, resting muscle tissue uses fatty acids for energy. Working muscle uses glycolysis. Glycolysis is in the presence of oxygen, aerobic respiration. Okay, and we go with anaerobic respiration, you put lactic acid, which shuts your muscle down. Heart muscles prefer ketone bodies to use as energy that's built up for energy for contractions. Okay. Under what conditions does the liver synthesize fatty acids and triglycerides? When there's extra. Okay. When excess fuel is available, the liver is going to synthesize fatty acids and triglycerides. Okay. That's how you get extra cholesterol in your body. What is the role of very low density lipoproteins in triglyceride metabolism? What does VLDL do? Okay. It's a carrier. VLDL complex transports triglycerides from the liver to your adipocytes. Okay. This is a major source of fatty acids that are used to produce triglycerides in adipose tissue. So very low density lipoproteins. Okay. This transports your triglycerides from the liver to your adipocytes. Okay. So the effects of insulin and glucagon on cellular metabolism. So insulin is secreted in response to high blood glucose levels. Okay. Remember, high blood glucose is high sugar in your blood. You produce insulin. Low blood sugar produces glucagon. They're both secreted by the pancreas. So insulin is secreted in response to high blood glucose levels. And then once insulin is secreted, you get carbohydrate metabolism, stimulates glycogen synthesis while inhibiting glycogenolysis and gluconeogenesis. So when carbohydrates are broken down, okay, the blood sugar is going to, so when you break down carbohydrates, you have a lot of sugars being broken down in the blood, right? Break down the sugars, okay, contain monosaccharides we talked about, and it stimulates glycogen synthesis. Glycogen synthesis is long chain glucose molecules that store, we have excess glycogen in the bloodstream. It inhibits glycolysis, so it doesn't produce more glucose or gluconeogenesis. So we've got too much glucose, that's where we're forming glycogen. So when glycogen synthesis is happening, glycogenolysis and gluconeogenesis are both prohibited because you don't want to put more glucose into the bloodstream because you already have it there. That's why glycogen synthesis is working, because you already have too much glucose in the bloodstream. Okay, and protein metabolism stimulates the incorporation of amino acids into proteins. Okay. Lipid metabolism stimulates uptake of glucose by adipose cells, and it forms triglycerides. So carbohydrates, when you eat too many carbohydrates, you form glycogen. When you have protein is metabolized, it starts forming amino acids and linking them together to form your proteins. It incorporates amino acids into the proteins. Lipid metabolism stimulates glucose by the adipose cells. And when you have extra fat, you form triglycerides from your diet. Glucagon and insulin we talked about, the exact opposites. Glucagon is secreted in response to low blood sugar. So when you have carbohydrate metabolism, it inhibits glycogen synthesis. Okay? Because you're breaking down your carbohydrates. Okay, you don't want to be storing them into glycogen. And it stimulates to adding glyconeolysis and gluconeogenesis. You want more glucose. So carbon metabolism, you're breaking them down and you're producing sugar in the bloodstream. So you stop glycogen synthesis because you need the carbohydrates, you need the glucose, and you get glycogenolysis, making more glucose, and gluconeogenesis, making more glucose. That's when glucagon is released. And then lipid metabolism stimulates the breakdowns of fats and ketogenesis. Okay, and protein metabolism has no effect on the glucagon or insulin reaction to it. Okay, so your metabolic effects. This is what insulin and glucagon do. Remember, insulin is released in response to high blood glucose. Glucagon is in response to low blood glucose. Okay. So insulin, cellular glucose transport is increased. Okay. You're taking sugar out of the bloodstream and putting it into the cells. Glucagon has no effect on glucose transport. Glycogen synthesis, making glycogen. When you have too much blood sugar, you want to get it out. So you want those sugar molecules to go into the cells and make glycogen. So you increase glycogen synthesis. Okay. And then glucagon, if you have low blood sugar, you want sugar in your blood. So you decrease glycogen synthesis. Okay. Glycogenolysis in the liver is decreased by insulin, because again, you have too much glucose. You don't want to make more glucose and produce in the stream. And it increases glucagon because you want to get the glucose out of the bloodstream, glucose back into the, you want to get glucose out of the bloodstream because you're producing glucose from the liver. So insulin's going to decrease that, glycogen's going to increase that. Okay, remember, because insulin, you're taking blood sugar out of the blood into the body. So you're going to decrease the formation of glucose. Glucagon, you have low blood sugar, so you're going to increase the formation of glucose in the liver, so it can release more into the bloodstream. Gluconeogenesis, the exact same thing. If you're releasing insulin, you're going to decrease the amount of glucose you make. If you're producing glucagon, you're going to increase the amount of glucose that you make in the bloodstream because you need to raise your blood sugar. Okay, so amino acid uptake and protein synthesis is increased by insulin. no effect by glucagon. Inhibition of amino acid release and protein degradation is decreased by insulin and no effect because you're increasing amino acid uptake. So you're not going to inhibit the amino acid release. Lipogenesis is increased by insulin. Breakdown of lipids to store energy has no effect on glycogen. Lipolysis is decreased by insulin, has no effect, and then increased by glucagon. And ketogenesis, which is a ketone body, is decreased by insulin and increased by glucagon. So glucagon, the basic thing is insulin is released when you've got to get blood or energy out of the bloodstream. You got to get those glucose molecules out of the bloodstream. Okay, and other things that produce more glucose you want to decrease. Glucagon, you got to get glucose into the bloodstream. You're going to start breaking down your fatty acids. Okay, so you're going to increase lipolysis, you're going to increase ketogenesis, the formation of things that can cause energy, that can cause you to raise your blood sugar level. Okay, so here's your antagonistic effects of it. You can see absorption of a meal, you have increased glucose. Increase in glucose causes an increase in insulin and a decrease in glucagon because there's too much sugar in your blood now. So you increase the insulin-glucagon ratio by forming more insulin, and you get the formation of glycogen, fat, and proteins. So what happens in the blood, it lowers the glucose, okay? Lowers amino acid, lowers the fat acids, and lowers the ketone bodies. It takes it out of the bloodstream. That's your absorption of meal. Fasting, you decrease your glucose in the blood. So you cause a decrease in insulin and an increase in glucagon. So your insulin-glucagon ratio decreases. You get more glucagon than insulin. So you get now hydrolysis of glycogen, fat, and protein. You're breaking them down to produce energy now because you don't have any in the blood. So in the blood, you get increased glucose, increased amino acid, increased fatty acids, and increased ketone bodies. So it's the exact opposite effect what insulin does versus what glucagon does.
Professor?
Yes.
Can you go back to that slide, but move the little colors
sure.
on the bottom?
Like that?
I was trying to take a picture of it. Yeah.
Oh, sure. No problem.
Okay, awesome. Got it.
Got it?
Yep.
All right. But just notice that these are the exact opposites right here. Exact opposite controls between insulin and glucagon.
Yeah.
So summarize the effect of the hormone insulin on carbohydrates, lipids, amino acids, and metabolism. So insulin, what it does, it stimulates the uptake of glucose. So when you eat a meal, you get glucose broken down from carbohydrates, insulin takes that and gets that out of the bloodstream into the cells. Okay, gets rid of glucose and the amino acids that have been broken up by the proteins. Okay, glycogen and protein synthesis, and so insulin stimulates the uptake. Let's start again. Okay, uptake of glucose, uptake of amino acids by the cells. Okay, you get the formation of glycogen, which is your monosugar units, and then it branches, and everything is your glucose unit. It says branched series of glucose units. That's how we store glucose for the body, is a form of glycogen. Okay, and protein synthesis. Okay, so it stimulates glycogen formation, stimulates protein synthesis, the formation of proteins from the amino acids that are being broken down by metabolism, and storage of lipids. The lipids are formed into triglycerides and stored in the body. Okay, so that's what it stimulates. It stimulates the uptake of glucose, uptake of amino acids, formation of glycogen, protein synthesis, and the formation of lipids. That's what's stimulated by insulin. It inhibits glycogenolysis, gluconeogenesis, breakdown of stored glycerides, and ketogenesis. So it stimulates everything that causes glucose to be stored out of the bloodstream. It inhibits everything that produces more glucose because you've already got enough of it. Does that make sense?
Yeah.
All right, perfect. Summarize the effects of glucagon. A lot of students get glucagon and glycogen confused. Glucagon is the hormone. Glycogen is the molecular compound where glucose units are linked to that are stored glucose units. So just don't get glucagon and glycogen confused. Okay, so glucagon is a hormone that opposes insulin. And what's its effects on carbohydrate and liver metabolism? Okay, so glucagon stimulates glyconeolysis, gluconeogenesis, and the breakdown of lipids and ketogenesis. So glyconeolysis produces more glucose. Gluconeogenesis produces more glucose. Breakdown of lipids is going to produce more glucose, and ketogenesis is going to produce more glucose. Glucagon, okay, is when you have low blood sugar. Okay. During low blood sugar, you want to do glycogenolysis, gluconeogenesis. You want to break down your lipids, and ketogenesis. All those are going to form increased amounts of glucose. You want to inhibit things that decrease the glucose in the bloodstream, like glycogen formation, glycogenesis. You want to stop it from forming glycogen. You want the glucose to increase in your bloodstream. So glycogen stimulates events or hormones that are released that will decrease blood sugar because you want to increase it. And then it inhibits those that would decrease your blood sugars, like glycogen.